So we've been learning all of these kinematic equations. How do we actually apply these in more than one dimension? How do we do 2 and 3D kinematics? Well, the traditional way that we look at this is in the form of a problem known as a projectile problem. So when we shoot something or launch something, maybe from a catapult. Okay, there are a huge variety of projectile situations. So you can't just memorize how to do it, but there is a general kind of structure to follow. Step 1, draw a picture. Very similar to any other physics problem that we've been solving. Step 2 is going to be write down the known and unknown values, but you don't want to just randomly write these down. I'm going to say write these down in a direction table, and we'll show you what this all means. And lastly, you want to look at your kinematic equations and figure out which one or ones you need to actually use to solve the problem. You might need to solve an intermediate value, an intermediate variable, in order to solve what you're looking for. But these 3 steps will work for every single kind of projectile problem. So let's go through an example and show you how this actually operates. So let's do an example. During a fireworks display, we have a shell that's shot into the air with an initial speed, so we have some initial velocity, 70 meters per second, at an angle of 75 degrees above the horizontal. So they give you an illustration. This is in your book, figure 4.13. But how would we draw this? Here we have our projectile being launched at some angle that is 75 degrees above the horizontal. The fuse is timed to ignite the shell as it reaches its highest point above the ground. And now we have to calculate some stuff. We have to calculate the height. We have to calculate how much time passes between the launch of the shell and the explosion. We have to get horizontal displacement, and we have to get the total displacement from the point of launch to the highest point. So from launch to the highest point. So we have a lot of stuff to do. So let's draw out this picture, see what's happening. We know projectile kind of goes up, and this particular one is going to reach its peak height, and then it's going to explode. Other kinds of projectiles might not do this. Other projectiles might continue going onward and fall right back down to the ground. Okay, so we can put some variables in here. We can put some values. We know that the initial velocity we have, v naught, is equal to 70 meters per second. We were given that, so that's what that velocity vector is. And any time we have things moving at angles, it's typically the case that we're going to want to break it into x and y directions. So I'm going to break this up into a triangle, and we have some little bit of this v naught. We'll call it v naught x going in the x direction, and we have some little bit of this going up in the y direction. We'll call that v naught y. Next, for the kind of question that we're asking, we want to write down all of our kinematic equations. Keep these all in mind. So commit these to memory. V final equals v initial plus acceleration times change in time. Change in x, change in position equals v naught times change in t plus 1/2 times a times the change in time squared. And then vf squared, the final velocity squared, equals v initial squared plus 2 times a times the change in position. These are our 3 kinematic equations. Always kind of want to keep these in the back of our minds. Now we need to make a directional table. So what does this mean? This means we break things into what's happening in the I direction and what's happening in the j direction. And with projectiles, we always want the same variables. We always kind of want to know what's the change in position in x, what's the change in position in y, what's the initial velocity in x, what's the initial velocity in y, what's the final velocity in x, what's the final velocity in y, what's the acceleration in x, what's the acceleration in y, and what are the change in times in each direction. So these are all the variables that are in these kinematic equations. And we need to figure these out and see which things we might actually know that we can plug in at the very beginning. Well, I already know what v naught x is. I know v naught x from this triangle that we see up here. I have, this is v naught x. It's the adjacent side with this angle of 75 and this hypotenuse of v naught. So in the x direction, v naught x is v naught times the cosine of the angle. And we can plug in the numbers that we have. We have 70 meters per second times cosine of 75. And when you plug those into your calculator, and you should do this, you will plug this in and you will get 18.1 meters per second. Make sure that you can plug stuff into your calculator. The final velocity. Well, it turns out in most projectile problems, unless we say otherwise, the final velocity is going to be the same as the initial velocity, 18.1 meters per second, because we typically ignore air resistance, so the acceleration in the x direction is 0 meters per second squared. So we know a lot of stuff that's going on in the x direction. Now what do we know about in the y direction? In the y direction, we don't know change in y, but we do know this v naught y. We're at the opposite side of this triangle. We have the angle of 75, and again, the hypotenuse of v naught. So this has to be v naught times the sine of the angle. And we can plug in all of our numbers. We have 70 times the sine of 75. And when you plug and chug those numbers in, you should get a 67.6 meters per second. So we have a pretty high y velocity. The final velocity in the y direction. What is this final velocity equal to? The final velocity in the y direction, when we come up to this peak, so as I reach this peak, this projectile, if it didn't explode, it would be traveling entirely horizontally. So that means it's no longer traveling up at all. It has to come to rest so that it can come back down. So the final velocity in the y direction, because this is at the peak, right, at the highest height that we reach, is 0 meters per second. The acceleration, we have gravity pulling this thing down, so the acceleration is negative 9.8 meters per second squared. Because it's the force of gravity that's acting to pull this thing down, and that acceleration due to gravity is 9.8 meters per second squared. And then we also have a change in time. Okay, so we know a lot of things already. We know a lot of these variables. Now we can look and we can start exploring, what do I actually need to find? So in part A, we have a change in y. Now how can I find this? How can I find the change in position? Well, I look up at my kinematic equations. So we can make a little chart of part A, part B, part C, part D, and see what kinds of equations, if these kinematic equations are useful. I look at the first kinematic equation, and in part A, I'm looking for change in position. I'm looking for change in y. There are no change in y's in this, so I would not use this kinematic equation. The second equation, I have a change in x, and I can substitute in change in y. These x's and y's are kind of interchangeable. If I'm trying to find the change in position in the y direction, I just make this a change in y instead. An initial velocity, I know what that is. I know the initial velocity in the y direction. Change in time, I don't know what the change in time is. The acceleration, I know what that is, and I still don't know the change in time. So if I wanted to find change in y using this equation, I would need to find t first, right, this t, and then I could find change in y. So maybe we want to come back to this, but let's look at the third equation first before we decide. And the third equation, okay, we have a final velocity. I know the final velocity. I know what that is. I have the initial velocity. Initial velocity, I know what that is. I have 2 times a, the acceleration. I know what the acceleration in y is. And then change in y, the variable that I'm looking for. So this is going to be the equation that I want to use. So let's use this equation. Let's use this equation in terms of y. So v final in the y direction squared is equal to v initial in the y direction squared plus 2 times a in the y direction times change in y. We want to solve for the change in y, so let's go ahead and do the algebra and reorganize this. So I subtract my v initial over to the other side, so I have v final y squared minus v initial y squared, and I divide that by 2 times ay to get this change in y by itself. So this step is algebra. We should be really good at this by now, and you really need to practice this to really get it down. You need to be able to do this algebra, and you need to be able to do it relatively quickly to be able to solve these problems. So we have a change in y that's going to be equal to the final velocity in the y direction, 0 meters per second, and we square that, minus the initial velocity in the y direction, 67.6 meters per second, quantity squared, and then we divide that by 2 times the negative 9.8 meters per second squared. I plug all of this into my calculator. And when I do this, I plug all this into my calculator and I get 233 meters for my change in y. So there's my answer. Let's keep going. Let's see if we can do part B. Part B, we are asked how much time passes between the launch and the explosion. So what's change in t? Well, now I know change in y. I know everything. I know almost everything here, right? I know 233 meters. So I have change in time I need to find. I know every single variable. I can pick whichever equation I want. So let's look at v final equals v initial plus a times change in t. All of these happening in the y directions. And I'm just going to choose this one because it's the simplest equation. It's the simplest version. I can use any of them though. It does not matter as long as it has a change in time in it. So let's solve this for change in time. V final y minus v initial y. All of that divided by ay is equal to my change in time. So I plug in all my variables. Change in time is equal to v final, which is 0 meters per second, minus v initial, which is 67.6 meters per second, all divided by the acceleration, which is negative 9.8 meters per second squared. And my change in time, when you plug and chug all these wonderful numbers in, is going to be 6.9 seconds. So that's how long it takes this projectile to go up to the peak of its path. What else do we have to find? There's more. Oh, the fun's not over yet. We have part C, where we need to find the horizontal displacement. So I need to find what is the horizontal displacement. I would need to find change in x. So I come over here, change in x. Now the nice thing about projectiles is I now know what this change in time is. So I can plug this change in time in for the y direction. So it's no longer unknown. It's now 6.9 seconds. And the nice thing is as long as your projectile and the nice thing about this is that typically the change in time is the same in the x and y directions. This is typically the only variable that'll be the same in both directions. So we can kind of use them for both cases. Everything else is direction specific, but the time doesn't care about what direction you're going. In part C, I want to find change in x. To find change in x, I can't use that first equation because it doesn't have an x in it. So let's look at the second equation. Change in x equals v initial in the x direction times change in t plus 1/2 times a in the x direction times change in t squared. This is already solved for change in x, so I don't need to do any algebra. Change in x is equal to v initial x, which is 18.1 meters per second, times change in time. The change in time is going to be 6.9 seconds. And then plus 1/2 times a, the acceleration is 0, times the change in time of 6.9 seconds squared. So that cancels out because of the 0. Change in x, if you multiply this all out, gives you a value of 125 meters. So there's my change in x. Great. Almost done with this problem. Almost making progress. What is the total displacement we need to find in part D? So part D, to find the total displacement, we kind of need to draw what this looks like. So in part D, we have this projectile. It starts off, and it travels a good bit in the x direction and a little bit in the y direction. Right? We travel in our path, we travel in both the x and y directions. So I travel over in the x, I travel over an amount 125 meters. And then I also travel some amount in the y direction. I travel up in the y direction to reach my peak. The distance in the y direction we found was 233 meters. So the total displacement has to be the hypotenuse of this triangle. So it has to be that little guy right there. And we have an angle that this travels at. So to find this displacement, we need to we use the Pythagorean theorem. Displacement equals the square root of the sum of the squares. So 125 quantity squared plus 233 quantity squared square root. Do that calculation and you'll find your displacement is equal to 264 meters. And what direction is this displacement going? So that's an extra question that they didn't actually ask, but we're going to find it anyways. So we have this triangle. We can pick whatever trig function we want because we now know all sides of this triangle. I'm picking the tangent. So the tangent is the opposite side over the adjacent side. 233 meters divided by 125 meters. So if I want theta, I take the arctangent of this. I plug it into my wonderful calculator. 233 over 125. Arctangent of that gives me an angle that's equal to 61.8, and that is above the positive x-axis. And this general approach of making these columns and figuring out which equations to use will work for any kind of projectile problem that you have to do.